So I would like to thank you all again for joining us today for Dr. Jude Kong's fascinating discussion. Before we get started, I just have a few items of business. Firstly, my name is Justice Allard. I am the Project and Administrative Assistant for the Sustainability Council. And I would like to start us off today by acknowledging that the University of Alberta respectfully acknowledges that we are located on Treaty 6 territory and Métis Nation Zone 4, a traditional gathering place for diverse Indigenous peoples, including Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, Anishinaabe, Inuit, and many others whose histories, languages, and cultures continue to influence our vibrant community. And in the spirit of using the land acknowledgement to personally reflect for a moment as someone of settler heritage on Treaty 6 territory, I think it's important to remember that the treaties are not just agreements between nations, but they're also inherently relate to the land we're on. We'll be talking about oil sands tailing ponds today, which are mostly located on land governed by Treaty 8. And of course, we have people on the call from all over the country, including Jude, and internationally as well. Regardless, though, I hope we can all use this opportunity to reflect on how we all have the responsibility to take care of the land around us, not just for its own sake, but for the sake of fulfilling the responsibilities we have to each other. It can be easy to forget sometimes, especially living in a big city, but nothing we have we have nothing which doesn't come from the land in some form. And so if we all have the right to a healthy ecosystem, and I believe we do, then we also all have the responsibility to not impinge on others' rights to the same, whether that be across the planet or just north of us in our own home province. Today's talk is part of the Sustainability Council Speakers Series. So during the academic year, the Council hosts interdisciplinary scholars, professionals, and activists who engage with sustainability, climate change, and the environment. Our lectures are usually held bi-weekly through the academic year, although after today's lecture and through till June, we'll be moving to a once-a-month schedule. You can find more information on our website at uab.ca/sustain, which is also, I just put in the chat. So just a few more notes before we begin. Firstly, we will be recording, or rather we are recording today's lecture and posting it on our YouTube channel, which you can find at UAlberta Sustainability. So for everyone here today, the recording won't capture people who are in attendance. It's only going to capture my screen and then Dr. Kong's screen as well. The audience will not appear in the published video. And there will be a Q&A to follow the talk. So if you have any questions that come up during the lecture, please put them in the Zoom chat and we will collect them from there. And then I will pose them to Jude following his chat or his talk. And now it's my great pleasure to introduce our speaker today, Dr. Jude Kong. So Jude is a professor at York University and the founding director of the Africa, Canada Artificial Intelligence and Data Innovation Consortium. Additionally, he is a member of the Canadian Black Scientists Network, a member of the Scientific Advisory Committee of the Mathematics for Public Health Network, a member of the Canadian Centre for Disease Modeling, and a member of the Canadian COVID-19 Modeling Rapid Response Task Force. Dr. Kong is an expert in artificial intelligence, data science, applied mathematics, mathematical modeling, infectious disease modeling, and mathematics education. During the COVID-19 pandemic, he's been leading an interdisciplinary team of more than 50 researchers from key academic and government institutions in 9 African countries that have been using artificial intelligence to help government and local communities to contain and manage the spread of COVID-19. In 2020, he won a York Research Leader Award, and in 2021, he was spotlighted among Canadian innovation research leaders for his work with the Africa-Canada Artificial Intelligence and Data Innovation Consortium. In 2022, he was spotlighted as a change maker by people of York University for his work in helping others learn mathematical concepts and encouraging them to find their passion and achieve more than they ever thought was possible. So without further ado, here is Jude Kong.
Thank you so much. Let me share my screen. Justice, thank you so much for the great introduction. You have said so much about myself that I don't think I would have been able to sell myself the way you did. You're a great guy. And to my fellow colleagues, friends at the University of Alberta, It feels like being home. It's just a few years ago, but because of COVID, it still feel like I'm part of the University of Alberta. Anytime I'm speaking, I still feel like I'm at the university, in the University of Alberta. And so go Pandas, go Golden Bears. I am a fan of the Pandas. I'm a fan of the Golden Bears. And so I miss them so much. And I'm always cheering for them. Go Pandas, go Golden Bears. So I'll be talking today about my work estimating and predicting greenhouse gas emissions from oil sands tailings pounds. And this is work I started actually when I was at the University of Alberta. And I'm really grateful to the University of Alberta Sustainability Council for inviting me to share this work, because this is what I'm passionate about, even though just like most of you, within the last 2 years, I have been mainly focused on COVID-19, which we all had to do whatever we're doing to ensure that we get rid, or we support our government and support governments around the world to contain and manage the spread of COVID-19. And that's what I've been doing for the last 2 years. But this is work I'm passionate about, which I've been doing, and I still have a team working on this. To start with, I would like to acknowledge, because the talk I'll be giving will be based on this paper, which I published with a couple of colleagues from the University of Alberta and some on retirement. And I want to acknowledge their work, How Wang from the Department of Mathematics, Tariq Siddiq, Renewable Energy, Julia Fort, Kathleen Semple, because who work with the government of Alberta. But I want to state that the government of Alberta have not reviewed our work, and so they have not endorsed, neither endorsed nor against our work. So I just want to state that even though Dr. Bokos worked with us, he was not representing the government. He was working on his own. And then as well as my colleague at the University of Alberta, and my mentor, Mark Lewis. Oil sands. What do I mean by oil sands, or what are we looking at here? And it's a great concern, and I think a lot of us from the University of Alberta will obviously know what oil sands is all about. But I just want to point out that, just based on the conversation we'll be having and where I will be leading to, just to point a definition of these, what it is. By oil sand here, I mean a mixture of sand, water, and bitumen. So bitumen here, by bitumen here, I mean it's oil that's still too heavy or thick and can't flow on its own. So that's what I mean by oil sands, this combination, and we'll find a lot in Alberta. So what happened with oil sands, and why is it a concern in our environment? If you look at here, this is a picture that's collected from Fort McMurray at the Athabasca area. And this is surface mining, or where we do around 20% of surface mining, and the rest of the 80% is in-situ mining. I'll discuss what that means later on. This is surface mining here in Athabasca, or around Fort Mac, around the Athabasca area. And what happened in this process, or within this region, as we'll see, not just in Canada, but around the world where we have this type of processes going on, is that because of oil sands, because you have the bitumen that's mixed with other things, we want to extract the bitumen. First of all, extract it from it. And then the second part is be able to make it liquid. I mentioned that it was very thick. And so you want to make it in a way that you can transport it to the processing factory where it can be taken, processed, and used for other purposes. So the first thing that we always need to do is, if we extract the bitumen that contain, as you have seen the oil sands, they contain a mixture of other things, we want to get the bitumen out of it. Most often water is added if we're doing surface mining here. But in situ, we just be able to make 2 wells there, heat it, and then ensure that it liquidify and get to a second one and become something we can transport. But I'm going to be talking about surface mining a lot here, which is 20% of the work that is done in our oil sands. Water is added to it. A diluent is normally added. The diluent here is because to break the hydrocarbon chains, since bitumen is kind of solid and cannot be transported through pipes, we want to make it a little bit liquid so that we can transport it through pipe. So you add a diluent. It could be, in Canada, we use naphtha and paraffinic solvents, most of our companies here, but you add something that will be able to break the carbon chains into it after extracting it. Once you add that to it, then you're able to recover the bitumen. It could be through gravity settling, because when in surface mining, when we get it, then we'll go and heat it through gravity settling. The bitumen will settle after adding this water and heating it, or through other means. we extract the bitumen, but then we try to recover the water to use again in the process. Another byproduct. Once we recover that, we send in, we create basins called tailing basins where we send in, or the tailing ponds, where we send in the byproduct of these process. And what happened is, yes, our goal is not to have the diluent escape with the byproduct or the bitumen escape with the byproduct. We are trying just to extract the bitumen and just leave the clay and other things there and get rid of them. But unfortunately, the diluent, which is mostly made of hydrocarbons, the naphtha, the paraffinic solvent, end up escaping here into our tailing ponds, which is a place where we have created to send in this byproduct so that they settle, they clear. The aim is to have the clay settle, and then we recover the water and use it back in the process. So they end up coming here in these tailing ponds that we have created. And this is the tailing ponds. So if you look at this picture here on my right here, you see this coming in here. So these are this byproduct coming into these tailing ponds. Unfortunately, the hydrocarbons do come in as well, and other things. Now, when these hydrocarbons come in there, or this byproduct comes in here, over the years, they settle down here. So they are to settle. Basically, you have the final particle that you cannot recover. Then they settle gradually. Once they settle down, then you recover the water, and then it becomes solid, and then you reclaim the land. Our government gives oil sands company 5 years or so to ensure the land is reclaimable. But unfortunately, over the years, because when this thing comes in here in these tailing ponds, there are bacteria that comes along with this. Over the years, the bacteria, they used the hydrocarbon, especially has been proven by my colleagues that most of the hydrocarbon comes from the diluent, the naphtha or paraffinic solvent. Over the years, the bacteria that's present in these ponds here, if you look at this, obviously bacteria will be present, break down these hydrocarbon, and unfortunately, that releases greenhouse gases into our environment. And that's a concern. And that may be one of the reasons why the council have given me the room to come and share this with you. But this is really a very big concern that we can look at in our country, in our province, Alberta. I still consider myself as somebody from Alberta, even though I live in Ontario, but Alberta is still home to me, from Alberta, to ensure that we address this issue. So the greenhouse gases are being emitted here. Even though when we recover the water and get it here, now the notion of the NP lake, which is something that started ago, was to ensure that you transfer, once they have settled down and you recover the water, then you now move them so that it becomes solid and you reclaim it, plant things to it, and become new land. That's the idea of NP lake that started more than 5 years ago, not long ago actually. But here as well, in the NP lake, the bacteria still continue breaking down the hydrocarbons and releasing greenhouse gases. In order to measure the greenhouse gases from this environment, what most of our oil sands company or the regulators, they do is they sample particular position randomly, and then they measure. And then they generate, once they sample those positions, for instance, you can assume that this is a surface area here where we are expecting this. You sample this point, sample this point, sample this point, you measure the point, and then you generally state that, oh, the methane or the carbon dioxide that is being emitted from that point, then you multiply by the surface area or something. Unfortunately, this is very biased. You can't have an exact value. And this is where mathematics come in, and this is where I will now move on to stating the objective of the work we have been doing. The work my colleagues and myself, I'm putting a team together, the team I've put at York University together is working on, which is, can we come up with mathematical model that can help give an accurate estimation of the greenhouse gas or any volume of tailings, and be able to project how long that will continue emitting greenhouse gases. That's something I'm doing. Our hope, by investing a lot of time, bringing a lot of resources, and bringing the best brain that Canada have into this issue, is that it will help our oil sands operators to mitigate tailing emissions and may assist regulators evaluating the trajectory of reclamation scenarios. That is our hope. Again, I must state that my work is in the preliminary. This work I studied when I was doing my PhD at the University of Alberta. The government of Alberta is not yet using my work. But that is the hope, and I'm working towards that to ensure that we have these regulators using these models, and I'm fine-tuning the models, working with my colleagues in other areas to ensure that we come up with a platform for our government to be able to use to inform when it comes to knowing how much greenhouse gases are emitted from oil sands tailings and being able to project that. So the work is based on this paper, which you may be able to find inside of Total Environment. Now, let's get back to our province or our country. In Canada, the oil sands are located specifically in 3 areas. You have the Peace River area here, you have the Athabasca area here, and then you have the Cold Lake area here. And this stretch between Alberta and Saskatchewan. Edmonton here, this is where my home is, as you consider Edmonton home, and I miss Edmonton so much. So this is the great city of Fort McMurray. And if you look at it, it looks very beautiful, but knowing the impact of greenhouse gases on our ozone layer and on our environment, how that in turn affect our environment, look at this beautiful city, you may start wondering how this will really affect our great Fort McMurray, because I'm looking at this beautiful city, look at the green vegetation here, and I'm like, oh God, I hope this doesn't happen, but it's happening. So, and we all have to bring our heads together and see how we can help solve these issues. I just thought I should summarize some of the things that happen in our oil company here. The surface mining in Alberta, just mining on the surface, not the in-situ mining, even though that's 20% of our mining, is probably the biggest mining operation in the world. I was looking at this, whilst I was preparing for this talk, I look at National Geography, and there's a picture here that was taken by this Ian Wilmer or something like that. And they clearly, leaving aside this, I'm not getting to the most destructive part of it, but I'm looking at the largest. So it is kind of the largest oil sands pounds that we have around the world. And he mentioned here, that's what caught my attention, that you can even see this when you're on space. So this is the one found in the Athabasca area. So he mentioned that while you're on space, you can be able to see these oils and pounds in the Athabasca area. And so that caught a lot of my attention. And I was just imagining, if that is that big enough, then how much greenhouse gases can it emit? And you look at this, the last time I checked the literature, the good thing is that our government take report of all of these. I realized the last time I checked the literature, it has a significant environmental footprint of approximately 895 kilometers square. Of this area, tailing ponds covered approximately 239.3 kilometers square, and the reclaimed area is only 19.2 kilometers square, leaving 220.1 kilometers square active pound structure. And this keep on emitting methane into our environment. So the total fugitive greenhouse gas emission from major oil sands operations in our oil sands in Canada as a whole, as of 2018, is approximately 2.2 million tons of carbon dioxide equivalent per year. Again, we all know the impact of this on our environment. I mean, seeing something as big as it is, no doubt that this is emitting this, but maybe through mathematical modeling, through statistical modeling, we may be able to identify diluents that will not be able to contribute to this. Maybe we need to move away from, I don't know if that's possible, but we need, as modelers, as researchers, to ask all these questions and see how we can sustain our environment. And that's what I love, why the Sustainability Council that we have at the University of Alberta, inviting speakers, diverse background, to be able to talk about these issues and see how we can join forces to address these issues. Very important. The first model I want to talk about is a model that was led by my co-author in the paper I wrote. This gentleman here at the University of Alberta, actually. This is the first mechanistic model that actually existed, and he coined the first approximation kinetic model to predict methane generation from oil sands tailings. This was authored by Tariq Slade and his student. And this was in 2008 when he was still a postdoc with Julia Ford. Julia here is one of my co-authors in the work I'm presenting here. In his model, it was a very simple model where he used the methane kinetic model. Instead of, he assumed just that, well, the zero kinetic model, he assumed that a change in the concentration of hydrocarbons. So if you look at this, after he established in the work he did in 2007 that most of the hydrocarbons or most of the greenhouse gases were as a result of the diluent itself and nothing else. By the diluent here, I mean either naphtha, depending on the diluent that's being used to cause, to actually reduce the carbon bonds in the vitamin so that we can transport it to the refineries. He modeled that using saying, okay, well, after identifying that the diluent is responsible for this, he assumed two models. The first part was that he assumed that a change in the concentration of those hydrocarbons is a constant throughout. By so doing, by change here, if you look at it, don't look at it in terms of mathematics, if you're not a mathematician, look at this as a rate of change of carbon in terms of time, but just look at it within time, every time, how is the hydrocarbon changing every day? If your time is in day, or every year, if the time is in every year, how is it changing? Well, he assumed that every year they are decreasing by a constant value, which he called K naught. Every year they will decrease. The negative here is just indicating that they are subtracting. They are decreasing every year. And this is the greenhouse gases being emitted here. So this is what he used here. He used this fact for the zero kinetic model that if they are decreasing by a constant value every year, then if I know how they have changed, then I can be able to use these equations here, which take into account the conversion efficiency, assuming that each time you break a hydrocarbon, how many moles of methane is being released corresponding to the moles of carbon dioxide. He was just estimating the methane being released from those hydrocarbons here. So he used the Boltzmann equation in order to estimate the quantity of methane that will be released when, if you assume that the hydrocarbons are being degraded as a constant rate. The second model that he had was the first order kinetic model. Again, in this model, he just assumed that the change in the concentration of the hydrocarbon, of the given hydrocarbon, there are many different types of the hydrocarbon in the diluent. What he assumed here was that the change in the concentration of the hydrocarbon is directly proportional to the quantity of the hydrocarbon present itself. By so doing, if he assumed a proportionality constant, if you're a mathematician, think of this as a change in the hydrocarbon being equal to, now this is the proportionality constant. All these can be related to the Monod function. If you're a mathematician, you're thinking of, or a microbiologist, and you're thinking of the Monod function. But by just assuming that, well, it depends on the number of hydrocarbons that are present, the less epsilon, you derive this from the Monod function. So his assumption was based on the Monod function that he come up with all these equations. But if you don't look at the mathematics and looking at what is happening, just assume that he is taking the hydrocarbon and assuming that they are being released for the zero kinetic model at a constant rate every year, depending on your time. And for the first order kinetic model, he assumed that they are being degraded at a rate proportional to the concentration. I think I just left out a negative that he had here. There should be a negative sign here because the hydrocarbons are reducing. And then from there, he was able to calculate the concentration of the total methane value by using this equation by summing. This basically is just summing. If you assume that the hydrocarbons have been broken down at a certain rate, when those hydrocarbons are broken down, a certain quantity of methane will be released. So he will now take those quantity of methane, and then he used a stoichiometric factor, which is basically from the Boltzmann equation, knowing exactly that when you break a hydrocarbon, you lose a certain quantity of methane. In addition to that, there was a lag period, which he took into account because he was using data from his lab. The idea there is that if you just introduced food to bacteria, bacteria is not used to that particular food. There will be a time period that will pass before bacteria become comfortable because they knew what they have been eating. So there's a lag period before they start breaking down the hydrocarbon. And so he assumed that there was a step function here, meaning that before a particular time, the bacteria is not breaking down the hydrocarbon. After that time, the bacteria start breaking down the hydrocarbon. At this point, he assumed that even though the bacteria was breaking the hydrocarbon and growing, I mean, it's a very nice environment, just bear with me. The bacteria needs to enjoy and grow, but he assumed that the bacteria population was constant. So now come to our 10, where we now decided to build on that model to come up with a more advanced model that take into account the stoichiometry of what is really happening, or the detail of what is happening in the tailing pounds. And so this is work I did when I was doing my PhD at University of Alberta, even though I completed when I was done, but I started when I was doing my PhD. In our model, what we did was, if we started with, let's first of all look at the process of breaking down, since my colleague Sidik had established that the methane is as a result of the hydrocarbons that are coming from the diluent. Let's look at breaking down those hydrocarbons. And so instead of assuming that the bacteria will break down the hydrocarbon, eat, and they will not grow, we say, no, the bacteria will grow. And so let's say, how would the bacteria grow? So the change in bacterial concentration, we assume it was due to growth, or they could die. They're changing. My colleague assumed that all this process was equal and they were not changing. And the hydrocarbon will be reducing because they are being biodegraded by the bacteria. But if we're still in the tailing pounds and not empty leg, there's continuous input. And so there's continuous input of hydrocarbon. And that's why I have this input here. All of these, when they break it, they release methane into the environment. How is bacteria growth model? Again, if you are bacteria, or if you think of yourself eating, your growth, look at this barrel here. Think of wine. What would determine if this barrel is full? It's not just this minimum point here. It's not this point up here, sorry. It's the minimum one here. If you turn around, what will actually determine where this is full? Because the moment it's reached here, it will start coming out. We'll say it's full. But if you look at this, if you were looking at from the other end, you said, oh, there's one here. So this is the top one. This is what would determine it's full. Or when it reaches the surface. No, actually what determines is the minimum one where it will start coming out. And so because the bacteria that lives in these tailing pounds rely on certain elements for its growth, the growth rate of the bacteria will be based on if enough of one particular element exists, the bacteria will not be lacking in that particular element, and so that will not affect its growth. What will affect the growth of that bacteria is the one that's limiting. And so we'll model this following this Lebesgue law of minimum law that take into account that the growth of the bacteria is based on the resource that's limiting. And we'll assume that bacteria will just die naturally. So this is how we model the growth. If I just, again, if you're not a mathematician, don't look at this functional form defining the growth based on whatever element is limiting. But if we assume here that nitrogen is limiting in the tailing pounds, in these are tailing pounds here, that is easy seen even from space. I'm not laughing anywhere because it's very serious. And that carbon dioxide here is equally another limiting element. And then if you look at these two, and if we decide now to say, well, the growth rate of the bacteria will be based on the minimum meaning that the one that is limiting. From here, we will be able to model the growth as a function, a minimum function of these functions, one depending on nitrogen and one depending on the organic carbon present in that particular tailing pound. And that's how we model the growth. We change the bacterial growth. Then for the bacteria, then we assume that data was proportional to concentration of bacteria. And so just assume one constant here, which is a proportionality constant. Bacteria will die here based on, if there are many more bacteria, more will die based on the population. And this is just the general law. Then we look at the degradation. Another point was to model degradation here. And in order to model degradation, what we did was that we assume that the growth rate of the bacteria will be proportional to the rate at which that bacteria is breaking down the hydrocarbon present in the tailing pounds. And if we decide to introduce a proportionality constant, it means that because we already established that the growth rate of bacteria was the minimum of a function that's driven by nitrogen and a function that's driven by the carbon, assuming that carbon and nitrogen are the two limiting resources in the pounds. So we assume that this is a proportionality constant. It means that the decomposition rate times this will give us this. From there, if we isolate the decomposition rate, then we end up with a function here that models the decomposition rate. And this is a conversion efficiency, where you break down the hydrocarbon and converting it to the biomass. Again, we use the monod form of modeling this. If you're not a mathematician here, do not look at this function here that model the total nitrogen in the system. Just look at it as the total nitrogen in the system. There's a function that captures that dynamics. We assume here that carbon will not be degraded at a time less than the lag time, assuming that the bacteria need a particular time to be comfortable with the new hydrocarbon being introduced into the environment before they start breaking that out. And by so doing, we have this lag time. And then for time greater than that, we assume that the bacteria growth rate based on the hydrocarbon will follow the monod form. Again, if you're not a microbiologist or a mathematician, just look at this as a function based on carbon that is helping the bacteria to grow with the food that they're eating. And so when we put that together, we have a series of equations. We don't look at a series of equations, but this is a series of equations that models the rate at which the bacteria, this is the bacteria, B here stands for the bacteria, and we look at the growth rate there, the dye, or the organic carbon here. For each of the organic carbon, there are many different organic carbon, but my colleague over the years have established that the organic carbon in the pound there will be based on, there are ones that are biodegradable. Some are recalcitrant and not biodegradable. Some are easily biodegradable. So my colleague Tariq had over the years established those that are biodegradable and keep on observing them. And when you take this, all of these biodegradable will be converted to greenhouse gases, and in order to estimate the methane from those greenhouse gases with the Boltzmann equation here, where this will give you the quantity of methane released when you biodegrade this quantity of carbon and this quantity of hydrocarbon. This is the quantity of methane that you get from there. So from there, we're able to estimate the quantity of methane. Then through the work, as I was mentioning so far, my colleague had actually identified the biodegradable paraffinic solvent as well as neither hydrocarbons through the work of the two of my colleagues that we did the work together, Julia and Tariq. And this is in their lab. They brought this in their lab and actually experimented. This is a picture I took when I was still in the University of Alberta. They estimated and realized from all the alkenes, they have the pentane, hexane, heptane, octane, nonane, decane, that those were biodegradable. Then from the Bitex compound that were present in the oil sands, the toluene, oxylene, or the M+, which is just changing between the xylene and where the M-xylene and P-xylene were biodegradable. And they look at the isoalkene, the 2-methylpentane, the 3-methylhexane, the 2-methylheptane, the 4-methylheptane, and the 2-methyl octane were biodegradable. So these are the hydrocarbons that we consider. There are many other hydrocarbons that we consider. First, we look at the biodegradation model and we fit that model to these hydrocarbons. And the model really captures the dynamics of all those hydrocarbons that were measured in the lab. These were just estimating it from the values measured in the lab. When we went forward to validate the model, we first of all started validating it and comparing it with the models that existed. We started with our zero kinetic model and first order kinetic model because those were the two mechanistic models that existed. And we used the same data that was used, the zero kinetic model and the first order kinetic model that was published in 2008. The data was collected in the lab for the hydrocarbons. And in collecting that data, methane was equally collected. And so even though it was collected for that, we used our parameter value that were estimated from using a different data source. And then we brought the parameter values here and tried to see if our parameter values could be able to capture the dynamics here. And what we found out was that when we used those parameter values, even though they were not estimating this, but for the zero order and first order kinetic model, all the parameter values estimated they were used in the same data that was used in producing the data for the methane was the same data for the hydrocarbons there. But with the neutral model, we're able to capture that dynamics, even though it was not used there, all the matches. Same with this other experiment, which uses synchronous mature fine tailings. And our model was able to capture the dynamics here. When we now move this data for the zero order and first order kinetic model in the paper published in 2008, the data there was the same data that was for the methane. But when we now move to a neutral data, which is the ambient mature fine tailings, paraffinic solvent, the diluent here is a paraffinic solvent, the diluent that was used here. So meaning that we're taking the hydrocarbons, meaning that we're taking the parameters from these paraffinic solvent. What we found out there was that the zero and the first order kinetic model do not perform well, but the stoichiometric model that take into account the dynamics of the bacteria still perform very well. And when we move to this other data set, this is the neutral data set where the data here was not used in estimating the parameters of the model, this is the CNR mature fine tailing, we realized that the zero and the first order kinetic model did not perform very well. These are zero, the blue here and the green here are zero and the first order kinetic model. The black here is the stoichiometric model throughout. The black performed very well, the red ones are the data. So the stoichiometry model captured the data in normal situations where we did not use it, the parameter from there or the data from there to estimate the parameter value. So in the neutral data. And if you look at this, you realize that when you calculate the goodness of fit using the normalized mean square error, you realize that stoichiometry model performed well across all the data sets, even though these were neutral data sets. Be it when you use the alkene, the BTEX, or the paraffinic solvent, or the hydrocarbon and paraffinic solvent as a whole, or all the hydrocarbon in NAFTA, the stoichiometry model that we designed performed very well. We tested the model with data in the field, methane measurement in the field, and what we found out was that for synchrot data here, Madrid Sivan Basin Lake, we realized that our model was able to account for 55% of the actual measured data in the field. This was now moving the model from experimental data into what is happening in the field so that we can be able to use the model in the field to project. And when we use it with synchrot Madrid Lake Sivan Basin Lake, we found out that our model was able to predict 50% of the total prediction. When we moved to CNR horizon, the 2006 data they measured, we could predict up to 95% of their measurement. And then for the 2017 CNRL horizon, we predicted 77%. For the Canada National Upgrading Limited 2016 data, we predicted only 17% of their emission, and for the 2017 data, we predicted 48% of the emission. What it means to us was that even though our model is able to capture this, we are only using the hydrocarbon that we identify as being biodegradable. We left a lot of hydrocarbon out, meaning that more experiments, and I think my colleague at the University of Alberta have been working on looking at these hydrocarbons to find out the ones that we had thought were recalcitrant or not biodegradable that have become biodegradable over the years. Our hope is that we'll be able to get this model to a point where we can be able to predict greenhouse gas emission. So in order to conclude, the stoichiometry model that we propose here significantly advanced over other models in the literature. The zero and first order kinetic model that Tariq had was one of the models that was the only model, mechanistic model in the literature that was doing a great job, but our model outperformed the zero and the first order kinetic model, and that's why we termed it the second generation model. When we applied the model to in situ or the field measurement, our results were hampered by the data that we had. We didn't have enough data in the experiment, and this called for more data to be measured in the lab. We have a big lab at the University of Alberta that's conducting that, that's looking at this, trying to identify the hydrocarbons that are biodegradable over the years and the recalcitrant ones. The model that we have here is very flexible. And so the hope is that as we perform this experiment and identify more parameter values, we just add it to the model and adapt it, and the model will be used. At some point, we'll be able to effectively estimate and predict the greenhouse gases that are emitted. And until such time, the stoichiometry model, as of now, can assist regulators and oil sands operators in ensuring that they are able to estimate and predict the greenhouse gas emission from oil sands tailing and NPIC lake as well. Thank you so much, et merci beaucoup à tous.
Thank you very much, Jude. That was a fascinating discussion. I feel like that was the most comprehensive education I've personally received on tailings ponds, which is, of course, an incredibly important thing, and unfortunately a feature of the Albertan landscape at this point. So very important for us all to know at home or abroad. So thank you very much. We've got some great questions from the audience. You've all been very engaged. So why don't we just dive right into it? We'll have about 10-15 minutes for Q&A if that sounds good to you, Jude.
That sounds so great.
Right on. Okay, let's see. Why don't we start with, well, we'll start with one of my questions first then. So it's something that you had mentioned in your conclusion, that this model is sufficiently, this is a better model and a sufficiently flexible model, so that as new inputs can be added in order to more accurately reflect and capture the greenhouse gas emissions from tailing ponds. And this should help regulators in considering these questions. Do you have any thoughts, though, on how to actually get the regulators to adopt these better models? As you mentioned, you had some collaboration with someone from the government of Alberta, but not actually the approval of the government of Alberta. So yeah, I don't know if you have any thoughts on this.
Thank you very much. I must say that our Canadian government has been the most transparent government in the world, in the sense that they make their data public. So the hope is that if they start working with academicians, where they are able to look at some of those results, my hope is that they will be able to adopt them. But I do think that in as much as Canada is one of the countries per capita emission, the highest in the world, the government is not just lying down. It's difficult for the government at some point to be like, you're championing climate change, and then at the same time, you are the greatest emitter of greenhouse gases. So this is something that's not balanced. But I do hope that with the present government and having a group like Sustainability Council, people like this could be able to push forward these policies. By events like this, by pushing for panel conversation that bring in people from the government, you get to a point, because at times the government is willing, they're trying their best, they're trying their best, but they may not know what to do. It just take academicians, people that understand what to do to solve the issues or to bring them to a better situation, in a panel conversation with them, in a conversation with them, to move them to the point where we are at the moment. You and I may be thinking differently from what politicians are thinking. They look at the vote, they don't look at the environment, they care about other things. But they equally care about survival. They don't want us to die. They care about us, even though they care about their vote, where the majority is going, they care about survival, they care about our country. Look at it that way. And so by being with them in the same room, discussing with them, pointing things to them, they would tend to see with you. My work in Africa, the work I do with the 9 African countries, proved to me that at times people don't do things because they don't know the right thing to do. The moment you sit with the politician on the table and you point to the data and you illustrate the illustration to them, they tend to understand with you. So I do believe that with the Sustainability Council, working with our politicians, our policymakers, we'll get to that point where if the Sustainability Council push forward policies, write white papers that indicate the implication of certain things and the way forward, and have that conversation, this broad conversation, stakeholder engaged conversation, we'll get there. The problem in our country here is that researchers speak to themselves. They don't engage the communities. They isolate the communities. Politicians speak to themselves and try to look for vote. But we need to speak to the people in the communities. We need to speak to the politicians, and everybody needs to have this conversation and find a way forward rather than blaming one or this or that person. It will not lead to the solution.
Excellent response. That was very well said. Thank you very much for sharing your thoughts on this. Did we lose you? Just looking through, I think we may have lost Jude here, everybody. We'll give him a moment to join again. These are the dangers of hosting these events on Zoom. When you're in person, you can't lose connection, but give him a few minutes here. Hello, Jude. I see you. I think we got you back in the call.
Sorry about that. I don't know what happened to my internet. Everything, my computer just died down, and
It's no problem. It's the inherent danger of hosting a Zoom event. When you're in person, as I just said to everybody, you can't lose connection, but you know, it's the platform. Oh, sorry. Yeah, well, why don't we still have a few minutes here. So let's, if it's okay with you, we'll try to get through some of the questions. Everybody, this has been very engaged. I don't know if I've ever actually seen this many questions come in. This is awesome. So we had a few sort of more technical ones from some of our participants. I'm wondering if you can speak to these. If it's not your area of expertise, of course, just feel free to say pass. But we had Kurt who was wondering, isn't a major problem that caustic is added during the separation process, which causes clay to become polarized into an emulsion, which does not yield to gravimetric separation?
Can you repeat that question again?
Absolutely.
Yes.
So Kurt is wondering if it's a problem that caustic substance is added during the separation process, which causes the clay to become polarized into an emulsion, which does not yield to gravimetric separation.
The problem is not that only that though, because the problem is that no matter what, the finer particles that escape contains the hydrocarbons. Because you try by all means, except we stop trying to convert the bitumen, which is kind of solid form, in a way that we can transport it, which will be difficult. We have to find it. But if once we try to do that, we end up with a diluent that we used. If this diluent escaped within the finer particles, no matter even clay is still there, but the greenhouse gases are not being emitted from the clay. The greenhouse gases are emitted because of the hydrocarbons that escape into the tailing ponds alongside the clay. The clay will settle down. We will reclaim the water, but those tiny particles of the hydrocarbons that escape are still there, and bacteria need food to eat. So that could be a problem, but this is for my work, for my colleagues' work, Tariq's work, not my work actually, because I'm not a microbiologist, but my colleague has been working on this. His work points out to the fact that it's actually the fugitive hydrocarbons that escape alongside the byproduct, the other byproducts.
Okay. Oh, thank you very much. Kurt, you've asked several questions, so we'll see if we have time to circle back to yours, but we'll make sure we have, we'll try to hit as many different people as possible. So we had Jesse who asked, this was relating to one of your earlier slides, where you had mentioned the 19,000 square kilometers of tailings that had been reclaimed. They were just wondering how, if you know how they had been reclaimed, and if you have a source discussing that you would be able to share. And maybe Jesse, you can get in touch, and if there's a source, I can get it from Jude, and then we can send it off to you. But
yeah. The Alberta Energy Resource summarizes it, AER. Just Google that, you find out the government of Alberta summarized this. This is that I look at. Again, the government do have good intention. I do hope that academicians work with the government, in the sense that you may have polarized things, but everybody wants to save our planet. They want to save our environment. And so the government has actually stated that within 5 years, everything should be reclaimed. No matter what, when you have a tailing pound, it should be reclaimed within 5 years. That's the government policy. Whether that is working, that's not working, because they introduced this idea of NPID legs, where you send that there. But the problem is that they do not realize that there are still bacteria present there that end up breaking the little hydrocarbons present, and greenhouse gases will still be emitted. But yes, there's a lot of reclamation land. If you go to Fort McMurray, they are reclaiming there and planting things, but it may not be significant because there are more pounds present. We all need to solve this problem. It's a very complicated problem, very complicated in the sense that based on where our economy is and the policies in our province, which change is difficult to come in, as you know. But all of us, we need everybody on the table to solve this issue.
well, thank you. Then you kind of actually touched on it here a little bit, but Hannah had made a comment that EPL's NPIT lakes are in reclamation, and they would assume that they're in the reclaimed category since they're no longer in use. And they mentioned Syncrude's FEN project as another interesting in-project reclamation. But again, you'd kind of mentioned that their question was, what are your thoughts on the status of reclaimed versus reclaimed status versus in reclamation status for NPIT lakes? If you wanted to speak maybe a little bit more to that.
Thank you. Yeah, I love the idea of the NPIT lake, but like I said, they still keep on releasing greenhouse gases. So they do not solve that problem of greenhouse gases. The faster they reclaim that, that's better. Somebody in the government had actually, and I've not verified this with the model, stating, well, it makes sense. Making smaller ponds will be easier because they may end up releasing less greenhouse gases. I have not tested it, but that could make sense. That somebody in the government had proposed that. But making that and then reclaiming that those little ones could lead there. But that doesn't stop greenhouse gases from being emitted. We could look into different diluents. Is naphtha or paraffinic solvent the way to go? I don't know. If you look at the work, all of them release greenhouse gases based on the hydrocarbon being broken down. But maybe at some point we'll be able to come up with a better solvent that will release less greenhouse gases into the environment. I doubt, but there are still bacteria that need food. So bacteria will only keep on eating, right? So it's a very complicated equation to solve. Very difficult one. NPIT lakes are good, but they still keep on releasing greenhouse gases.
Absolutely. It is certainly a very complex question. Miguel was wondering, so Miguel's question was, how many greenhouse gas emissions do we save if we don't send tailings to the ponds? So maybe another add-on question to that would be, are you aware of other methods of dealing with tailings? Or did any of that come up in your research?
Well, in our country, we do two types, right? There are two types of mining. You have the in situ, and then you have the mining, which is just mining, surface mining. Now, if the oil sands is less than 70 kilometers deep or something like that, you just, I think 75 kilometers deep, you just do, you do surface mining. But when it's more than 70 kilometers deep, you extract it there. That in situ extraction does not release greenhouse gases in the environment. Because what you do there is that you create two wells, one on top of the other one, and then you hit the first one, kind of gravity hitting, and then the bitumen will melt and then fall in the second one, and then you take it away. That doesn't solve the problem, but there's still surface mining, and surface mining will end up in a situation where we need to be able to separate the bitumen from the clay and the other things. Once we're doing that, we end up in a situation where we use a diluent that end up being broken down by the byproduct escape, then bacteria breaks them down, releasing greenhouse gases in our environment. Yeah, but the in situ mining, I will say clearly, they still release greenhouse gases when in the factory, there are other processes, but not the process, you don't have the fugitive hydrocarbon escaping because they're doing there on the spot, and you just need to dig two wells.
Yes, absolutely. Yeah, it's being noted in the chat here, of course, that your work, to clarify, is primarily focused on greenhouse gases. There are certainly other toxic elements that are involved in tailings that can leach out into the water supply, and we have seen health effects of that in northern Alberta. But you're working on the greenhouse gas side of things. Okay, we probably only have time for one last quick question. So maybe I will take my moderator privileges and we'll close off with a question I had. And it's something that you'd mentioned in the early portion of your presentation, how important it is, and at the end as well, to have people from across disciplines seeing themselves and their knowledge as important in addressing these sustainability and health challenges. And then, of course, for researchers and politicians to engage with communities outside of academia as well. So I'm wondering if you have any closing thoughts on how we can foster this sort of collaboration or engagement, whether that is, across disciplines or with our communities. Yeah, I'm wondering if you can speak to that a little bit.
Thank you very much. Speaking to that, I will take the blame first of all. When I designed this model, I never got any community involved. I got my colleagues from the government feedback, but not the government giving me feedback. Co-design models with the communities. You can't solve a problem of the community on your own, sit on your decks and think that you know the solution to the problem the community is facing. You need to get the community involved in designing a solution to that problem. You're a tool and used by the community to co-design the problem with the community, with all stakeholders, including the government. That's the way forward. So I take the blame. I am part of the problem because I designed my model without the community involved. But the way forward is we co-do it with people that live in Athabasca, with people that live around those areas, and do everything with them. Once we do that, we will move to a point where everybody understands what is happening. If it is a problem that we have to face as a country and find solutions, everybody knows that we are fighting, everybody is trying.
That's, well, those are wonderful closing thoughts. Thank you very much, Jude. And I think that really wraps in with some of the questions that we're having here in the chat as well. So yes, that's amazing. Co-design models with communities. I love that. That's a great take home. All right, well, thank you all for joining us today. Thank you so much, Jude, for your wonderful presentation. We're happy to virtually host you back at the University of Alberta. Please, of course, we'd love to have you back anytime you're interested. As a reminder to everyone on the call today, this was a part of the Sustainability Council Sustainability Lecture Series. We will be having one coming up in 2 weeks on April 13th, featuring Ashley Consuelo from Memorial University, and she'll be discussing climate grief. So you can find more about our upcoming lectures at our website, uab.ca/sustain. And I'd like to give another huge thank you to Jude Kong. Thank you so much for joining us today.
Thank you so much for having me. I feel at home. Go Pandas, go Golden Bears.
Design models with communities and go Pandas, go Golden Bears. I love it.
Nothing about the community without the community, my friend.
Absolutely. Absolutely.